There, got it into slideshow motion. All right, so we're going to cover rotational motion, and instead of doing just a PowerPoint, I thought it might be advantageous to just talk through it a little bit. So if you can tolerate my voice just a little bit longer, otherwise you can turn the sound down. All right, so we want to first focus on the kinematics of rotational motion, and I like to start with kind of looking at this ladybug simulation. So there's some words here, but I think it might be better to actually show you the sim. So here is the ladybug going around, and if I give this ladybug a little bit of a spin, you can see, and I'm going to pause it as we go here, this green arrow is indicating the linear or tangential velocity. It's rotating at a constant speed, and it has a centripetal acceleration directed towards the center. So we let her play, and we can see that, again, linear or tangential is tangential, and it's constant. So now what I wanted to show you is what if we have two objects, and this is like a stink bug or something, and I'm going to give it a certain velocity and get it going here. Oops, yeah, hit play. I'll hit pause, and you can see that the time it takes this ladybug to complete one revolution is the same amount of time that it takes this, stink bug or whatever it is to complete one revolution. So obviously the bug on the outer edge has to cover a greater distance in the same amount of time, so it's going to have a greater linear or tangential speed. So even though this is moving at a constant speed, it depends on how far away you are from the axis of rotation to how fast it's going linearly or tangentially. So what if we want to describe this rotation motion and somehow call anywhere along this radial line has the same velocity? Well, we would call it the angular velocity. So the angular velocity, the angular distance that this travels, which is 360 degrees, for both the ladybug and this beetle is going to be the same. So we could say that the ladybug and the beetle have a constant angular velocity because they're covering the same rotation in the same amount of time. So that's kind of the premise for what we're going to be looking at here for the ladybugs. And that's what I just said before. So we want to talk about those relationships between the two. All right, no, I'm not. There we go. Okay, so this key to the rotational motion, everything we've done so far, kinematics, dynamics, energy, has a rotational equivalent. So if you remember what we did before, you just have to be good with the variables and the slightly different vocabulary. All right, so let's look at what we had from the linear world. So we had x represented position, we have displacement, velocity, average velocity, and linear acceleration. So in the rotational world, we use theta to stand for an angular position. Delta theta is the angular displacement. Omega is the angular velocity or angular frequency, and this would be an instantaneous angular velocity, angular frequency. And then we have average velocity, average angular velocity, and our angular acceleration. So we had A for linear acceleration, and we use this symbol right here that looks like a fish is called an alpha. This kind of curly W is called an omega. And I think everyone is familiar with this guy right here. That's the theta. So we're going to kind of go through how do we kind of go back and forth between the two. Ooh, I spelled that wrong. Have to fix that. Okay. All right. Degrees versus radians. First of all, the SI unit for theta is going to be radians. So yes, I know we have been dealing in degrees all the time. We will have to switch back and forth between degrees and radians, so keep mindful of that. So you should know how to go convert degrees to radians. So 360 degrees equals 2 pi. That's supposed to be a pi looking thing, equals radians. And sometimes you might see units of revolution, so 1 revolution all together. So something you may have already seen in a math class, but we're expecting you to know this in physics. So the big question I get is, how do I know when to use degrees or radians? Well, if you have to do components and you're using trig and x and y components, then use degrees. If rotational motion is involved, radians is going to be the standard. So that's pretty much the rule to follow in that regard. All right, so if we want to look at the angular displacement delta theta, oh, my picture disappeared. Oh, well, it's a very nice circle. The change in angular position is equal to the arc length. So what this picture was supposed to look like is if I had an object that started right here and traveled along here, then this path, this angular path, is also called the arc length, and it's usually labeled S, little s for the arc length. R represents the radius of the circle. So if I want to convert this arc length, which is measured in meters, I just take the radius of the circle times theta in radians. So that's how we convert a distance to a angular measure in radians. Oh, there's my picture. Oh, I just need to hit the button some more. Okay, so we got that. All right, so usually the theta is dropped. You got to remember this is not on the AP equation sheet. You must memorize the relationships for linear to angular. All right, angular velocity. Again, this symbol is omega. And just like before, where average velocity was the change in position over time, it's the change in the angular displacement, or I'm sorry, just the displacement, angular displacement over the change in time. So if we want to find the instantaneous angular velocity, just like we did before, we take the limit as delta t goes to 0, and you get the instantaneous or linear tangential velocity is equal to r times omega. You can also do this by finding the slope of the tangent line of the theta versus t graph, just like before if we took the slope of the tangent line of the x versus t graph to find velocity. So again, everything is the same here. Okay, and again, SI units is going to be radians per second. Theta or radians is viewed as kind of a dimensionless unit. So if I take r, which is measured in meters, times omega, which is measured in radians per second, then I would get a linear velocity of meters per second. So if you kind of forget how to do this or how this equation looks, just think of the units and remember that radians are dimensionless. All right. Oh, yeah. So additional units you can also see would be RPMs, rotations per minute, or revolutions per second. So there's a variety of different ones, but radians per second is the SI unit. All right. Angular acceleration is this symbol here. It looks like a fish, is an alpha. So angular acceleration, just as we did before, is the change in angular velocity over the change in time. So final angular velocity minus your initial angular velocity, just like we've done before. And the relationship between the linear world, or this would be the tangential acceleration, or the linear acceleration, is equal to r, the radius of the circle, times your average acceleration. The SI unit, again, radians per second squared. As in the past, numerically, we deal only with constant angular acceleration. So this bar over top, sometimes we don't leave it in there at all, or might not even call it average angular acceleration. But conceptually, if the acceleration was varying, we would look at the limit as delta t goes to 0, or once again, the slope of the tangent line on an omega versus t graph. All right, so once again, if you remember the linear and rotational analogs, you already know rotational kinematics. The kinematic equations for angular motion are exactly parallel to the ones for linear motion. The biggest thing in here is being very mindful of the vocabulary and using the right words. That's the part I can tell you, but I can't learn it for you. All right, so here's the two that we've talked about before, average velocity and average angular velocity. They look very much the same. This would be our first equation of acceleration is the change in velocity over time. Same thing for omega. Look, they even look similar, so it's easy to kind of put them together. The second equation also has its rotational analog. And of course, this one that kind of looks like an energy equation. Same deal, nothing really has changed much. So as I mentioned before, be mindful of vocabulary. You can't just say the velocity of the object. In this unit, you need to be very mindful in calling it the rotational velocity or angular velocity. Use linear velocity or tangential. So linear and tangential are the same thing. Angular velocity or angular frequency is also the same thing. So similar ideas with displacement. Make sure that you're talking angular displacement if you need to. The one that's a little bit more confusing is acceleration, because we do have a lot of different types of acceleration, including centripetal acceleration. So centripetal, also known as radial acceleration, can also be expressed in terms of angular velocity. So if we remember this from before, our radial is the same as another word for centripetal is v squared over r. This is on your equation sheet. If I substitute in that v equals r omega and I square that, I can simplify the centripetal acceleration can be written in terms of the angular velocity, r omega squared. So that also has its rotational analog. And also, just as a reminder, the total acceleration is the vector sum of the centripetal and the tangential acceleration, and we've talked about that before. So that is the centripetal acceleration. And all right, the direction of vectors in rotation. So in the AP world, something that is counterclockwise, and we'll use CCW to stand for counterclockwise, is deemed as the positive direction, and clockwise, which is CW, forgot that, is the negative direction. Now, so if you go moving on into the collegiate level, physicists will use something called the right-hand rule to establish the direction of a rotational variables. They call them pseudo-vectors. So it's either direct, they establish that direction as either into the page or out of the page. So the right-hand rule, as you can see in the picture, if you just take your right hand, so first thing is you need to know which is your right hand, and your fingers will follow the direction of the motion. So if this thing is rotating, as I view from the top down counterclockwise, my fingers follow the direction of motion, and then my thumb will point the direction of the pseudo vector. So in this picture, the direction of the average angular velocity would be straight up. And again, here, the right-hand rule would go down. So if we don't usually draw two-dimensional this way, so usually things are rotating in the plane of the page. So the direction of the pseudo vector would be either into the page or out of the page. So if your thumb points out of the page and you're pointing at you, that is considered the positive direction, and that would correspond to counterclockwise. And if you have a motion that is clockwise and you follow with your fingers, your thumb would be pointing into the page, and that would be deemed the negative direction. So right-hand rule, we'll be talking about it. Why does it matter when we get into things like cross products? But again, not so much in AP world, but I did want you to see it a little bit. All right, the last thing we wanted to talk about, as we talk about things that rotate, we also are going to eventually get to things that are rolling across the floor. So these relationships between things that rotate and things that roll are very similar, because we have these same kind of relationships between the linear world and the rotational world. So if we look at this tire, if it rolls along the floor, then this arc length corresponds to a linear distance, as long as, and this is the part at the bottom that's important, that this object rolls without sliding. So as long as it rolls without sliding and kind of maintains contact with the floor, then all of these relationships are true. And this actually becomes very important. And this is called the non-slip condition. And we will be talking a lot about the non-slip condition, but I wanted to introduce it here. So that's it with rolling motion. Your textbook, Chapter 8, has a lot of practice problems with looking at the kinematics and solving some basic problems. So check on the Canvas modules for a short online assessment to making sure that you can use the formulas.